Previous case is that we consider for the Zeeman effect without spin, and in this class, here we consider for the spin, Zeeman effect with the spin, Zeeman effect with the spin. Here, then the magnetic moment, atomic magnetic moment. In previous case, we only consider for the orbital contribution of magnetic moment, but here we should consider for the spin. We call it is anomalous Zeeman effect. Actually, the anomalous term is not valid in this case, because anomalous means that very not normal. But in general, when we do the experiment by the Zeeman effect, and because we should consider for the spin, and it is a normally observe the anomalous Zeeman effect, not normal Zeeman effect, and this terminology is only from the theoretical calculation, and it is more realistic. So I think that it is not abnormal, but it is a normal Zeeman effect, and normally we should consider for the spin. We should consider for the spin magnetic moment, and the spin magnetic moment in the orbital magnetic moment is written like GL and the E over 2 ME and the orbital quantum number. But here in the spin case, and the minus spin originated from the electron, and it is L orbital in this electron, ME, and the E over 2 ME and spin. And the different thing is that like that minus E over 2 ME is common, and the GL plus GE spin like this. It is for example, it is the electronic gyromagnetic ratio. Electronic gyromagnetic ratio is 2 in the electronic gyromagnetic ratio. And the interaction Hamiltonian, can be write down like G prime is that minus mu dot B. So it is mu and mu is like this. So it is like mu B over H bar, and G L plus GES dot B, because in this one is that Bohr magneton divided by the H bar. So and here, because also we already assume that the magnetic field is along the G direction, so it is constant magnetic field, and mu B over H bar and the GLG, and along the G direction, so GESG. So because magnetic field is the G direction, and it is realistic, and also we should only consider for the fine structure also. Here, then the first thing is that we should consider for the weak magnetic field. Weak magnetic field case is generally can be accepted, and because magnetic field is weak, and fine structure fine structure can be dealt with the zeroth order state. The fine structure. From the basic idea of the perturbation theory is that Hamiltonian consists as a unperturbed Hamiltonian plus perturbed Hamiltonian, but in previous case, we deal with the fine structure like relativistic effect or the spin-up coupling effect can be dealt with perturbation Hamiltonian. But here, after calculating the perturbation Hamiltonian, and it is a solved Hamiltonian, even though it is a first order. Then even though it is solved by first order, then with a second order, and that is already calculated. And H0 means that calculated Hamiltonian. It is well defined quantum number. So in this case, and previously we studied for the fine structure of the hydrogen. So anymore the fine structure Hamiltonian does not deal with the perturbed Hamiltonian anymore. So only include the zeroth order solve the perturbation. So and the Zeeman Hamiltonian in this case, and only the Zeeman Hamiltonian consider for the perturbation energy, and also this one it is a fine structure. For example, it is a fine structure in previous case, and we can treat as unperturbed Hamiltonian because we already studied the fine structure case. And so fine structure can be dealt with H0, and it means the zeroth order, even though it is a perturbed Hamiltonian from the ground state Hamiltonian. And also here this Zeeman Hamiltonian can treat as a perturbed Hamiltonian because it is a weak magnetic field. A weak magnetic field means that it is weaker than the fine structure, weaker than the H0 plus H prime. So even in this case, and it is a small term comparing with this original Hamiltonian. So and also then we should use that the basis in previous case NL. Here we should consider the spin S, and the ML and MS. We should use these bases because all of the quantum number is that the NLS and the corresponding L and S magnetic quantum number. So then here in this case, and there are two bases. One is that coupled basis, or the uncoupled basis. And here it is uncoupled basis, and the coupled basis means that here JMJ is that spin-up coupling. In the spin-up coupling makes that the total angular momentum J. So in the J is that the total angular momentum, and the MJ is the corresponding the magnetic quantum number. So it is a coupled basis. And the coupled basis can be expanded like uncoupled basis. So in this case, and there are so many in general. These coupled bases can be expanded like uncoupled bases, like ML MS summation, and here NLS ML MS basis, LS ML MS basis, and JMJ. And so here it is a completed set in terms of the orbital quantum number and spin quantum number and corresponding the magnetic quantum number. And here this expression we call it is Clebsch-Gordon expansion. This Clebsch-Gordon expansion is written in the textbook, and it is very delicate calculation. And in the table 11 in the textbook, 375, and there are several tables like Clebsch-Gordon coefficients for J1 and for various J1 and J2 case, and there are several Clebsch-Gordon coefficient. It is already calculated, and this calculation is tabulated in the textbook. So I did not write all the Clebsch-Gordon table, but when you use this, and you should use the table that corresponding to the J case. Then when I in the table 11.3, there are Clebsch-Gordon coefficients. For example, in the in the hydrogen 2p state. 2p state means that the principal quantum number is 2, and the orbital quantum number is 1, and the spin is basically 1/2. So J is that L plus minus S. Then the L plus S means that the third half. L minus S is that 1/2. So there are two possibilities for the J equal to 2/3 and 2/2. Then in the Clebsch-Gordon coefficient case, and the basis is the J and M, whether J or MJ. In this case, in the J and MJ case, and for example, if the J is that the third half, and the MJ is that there are various MJ, then 1/2 minus 1/2 and minus 3/2. It is case for the J equal to 3/2. Then another case is the J equal to 1/2 case. 1/2 case, and there are two possibilities. One is that 1/2 and minus 1/2. Then like this, and this because it is a matrix, in the matrix case, here M1 M2 case, and here one means that two electrons makes that the 1/2 and 1/2 plus. It makes the one case, and then it is 1/2 and the minus 1/2. For 0 case, also 1/2 and minus 1/2 case, and for minus 1 case, 1/2 and minus 1/2 case. In this case, and in the table in the textbook, here the Clebsch-Gordon coefficient not 11.3, 11.4. It is J1 equal to J3 half, J2 equal to 1/2 case. I'm sorry. I'm sorry. It is not. I'm sorry. I'm sorry. Here. It is. It should be revived. Okay. Okay. Here is 11.3 is okay. Yeah, it's okay case. Then in this case, and the coefficient is 1, 0, 0, 0, and 0, 0. There is 0, 1 square root 3, 1 over square root 3, and 0, 0, square root 2 third, 0, and 0, square root 2 third, 0, 0, minus 1 over square root 3, and 0, and 0, 0, square root 2, 3, 0, 0, 0, 1 over square root 3, 0, 0, 0, 0, 1, and 0, 1 over square root 3, 0, minus square root 2 third, 0, 0. It is tabulated. This table, it makes that hydrogen 2p state. It means that it is Clebsch-Gordan coefficient. Clebsch-Gordan coefficient, for example, in the basis, this basis, how can I write down? For example, in this case, for the J and Mj has the basis 3/2 and the 1/2 case. It means that J equal to 3/2 and Mj is 1/2. This line, Then other terms is 0. Other terms are 0. Only the non-zero term is like this. Non-zero term is like this. And in this case, and 1 minus 1/2, and here is a 0, 0 1/2. So then okay. Then it can be expanded like M1 and M2, and here the case LS M1 M2 and LS M1 M2 as basis 3/2 1/2. Then here in this case, here L equal to 1. Here L equal to 1 and S equal to 1/2. So is LS is the L equal to 1 and 1/2. 1 and 1/2. So then there are in the M1 M2 non-zero M1 M2 is that the 1 minus 1/2 and the 0 and 1/2. So and from the Clebsch-Gordan coefficient, here in this basis there are two non-zero bases is like 1 1/2. M1 is 1 and the minus 1/2 basis. This basis is like this. It is the coefficient is minus is the 1 over square root 3. And the second basis is that M1 0, M2 1/2. This coefficient here. So square root 1 1/2. 0 1/2 basis like this. So and this Clebsch-Gordan coefficient we do not calculate it in more detail, but because it is very tedious and tedious calculation. But Clebsch-Gordan already tabulated. So when we use this table, and we can make that the non-zero basis. This here in this hydrogen 2p state makes that J equal to 2/3, 3/2 and 1/2. 3/2 case there are 4 levels, and 1/2 case and 2 levels, and it makes that matrix M1 M2 case, and there are this kind of matrix can be tabulated in the Clebsch-Gordon coefficients. And also in this case J and Mg, for example, it is an example. If it is J equal to 2/3 and 1/2 case, one example is this expansion. Then the non-zero expansion is 2 terms. When he makes that 2/3 and minus 1/2, the non-zero term is coming to this, and the basis should be in the 1/2, and the 0 minus half, and the minus 1/2, and these two coefficients should be corresponding to this one. So then for example, another example is that it is 1/2 and 1/2 case. 1/2 and 1/2 case is that here this line is that the non-zero term coming from this term and this term. So here the coefficient is that 2/3, 1/2, and it is 1 minus 1/2, and plus it is minus 1 over square root of 3, and 1/2, 0, 1/2, and like this. This matrix elements, this basis can be expanded like this from the coupled basis in terms of uncoupled basis matrix elements. Here we should consider basically the Hamiltonian interaction Hamiltonian is like this. Because GL and G is constant, we should calculate for the expectation of the LG and SG. So we should keep in mind this Hamiltonian. So as an example, and the 1/2 basis and the LG expectation, 3/2 and the 1/2 basis. It is a basis can be like this, and the 1/2 basis is here, and the 3/2 1/2 basis, 3/2 1/2 basis expanded like this, and it is an example. So it is 1/2 basis is that the square root 2/3, 1/2, 1 minus 1/2, minus 1 over square root of 3, 1/2, 0, 1/2. It is 1/2 basis, and multiply LG, and 3/2. This 3/2 1/2 basis is here. So 1 over square root of 3, 1/2, 1 minus 1/2, plus square root 2/3, 1/2, 0, 1/2, and this basis. Then only this expectation makes that here we should keep in mind that here it is ML and it is MS. It is ML and it is MS. Then we can expect that LG operation onto the it is orbital. So orbital operator applied to 0, then it is a 0. So we cannot consider here. And the LG makes apply to the 1. It is a H bar. So and only this term, the other one of expectation between this term and this one is it is orthogonal, so it is a 0. And this one multiplication also 0. So only this one and this one equal to 1. So and only survive the term multiplication of this one and this one. So it is square root of 2 over 3 half. Okay, it is like this. For example, like this. Then basically, and also NLS ML prime and MS prime and LG expectation NLS ML MS is that it makes that ML H bar and the other one should be diagonalized, and Kronecker delta ML ML prime Kronecker delta MS prime. Likewise, in the NLS ML prime MS prime apply to the SG NLS ML MS. It is MS H bar Kronecker delta ML prime Kronecker delta MS prime, like this. So then we should consider it is one example of the expectation value of the 1/2 and this one and this term expectation. So every kind of expectation on the coupled basis is that it makes that this relation. So and then it related to the Clebsch-Gordon coefficient. So we should make a table, and basically, and it makes that the H bar is a unit. So and we should make that LG over H bar has a matrix. And how can write the matrix elements? And it related to the Clebsch-Gordon coefficient, like this kind of calculation. So there are in the J equal to third half case, and there are 4 kinds of third half: 1/2, minus 1/2, minus third half. It is case. And also if it is 1/2 case, there are 2 possibilities: 1/2 and minus 1/2. Then here this basis is a coupled basis for the J and MJ. It is a J and MJ and LG and J and MJ. It is a coupled basis with a spin, considering the spin-up coupled basis, but it is not coupled basis. It is uncoupled basis. Uncoupled basis defined in each L and S. So here we are interested in the coupled basis expectation value. So and the other in the this also same 3/2 case, 3/2, 1/2, minus 1/2, and minus 3/2. Then also in the case of 1/2 case and 1/2 minus 1/2. Then here, for example, in the 1/2 for 1/2 is that this line, and the 3/2 for 1/2, 3/2 for 1/2 is this line. In this line, and the coefficient is like this. So it is kind of square root 2/3, like this. And in like this, in each table we can calculate. so many calculation needs, and it takes very long time. But it is just one example. It is just one example of these two bases. So the result of these bases, I will write down 1, 0, 0, 0, 0, 1/3, 0, 0, 0, 0, minus 1/3, 0, 0, 0, 0, minus 1, and 0, 0, square root 2/3, 0, 0, square root 2/3, and 0, 0. And in this case, 0, 0, 0, 0, 0, square root 2/3, 0, 2/3, 0, 0, minus 1/2 third. Then here, then when you see this, and it is 4x4 matrix, 4x4 matrix, and it is also diagonalized, and it means that this term makes that J equal to 3/2 subspace. J equal to 3/2 subspace, but also it is already diagonal. And also 1/2 basis is this one. It is the J equal to 1/2 subspace. Other terms of diagonal, the other terms is not physical in these 2p states. And also here we are interested in the J equal to 2/3 subspace and the J equal to 1/2 subspace. So, and we need to this kind of things. Okay. When I described briefly, and this we already calculated the Gman energy Hamiltonian, and because this Gman energy Hamiltonian, it can be treated as a perturbation in the weak magnetic field case, and basically, and this we can make that fine structure as the zeroth order Hamiltonian and solved Hamiltonian, and the fine structure is a result of the relativistic effect and spin-off coupling, and so we should make a basis at a coupled basis, because J means that coupled spin-off coupling, and the spin-off coupling basis should be considered here. But in the magnetic field, the Gman Hamiltonian case, and we should calculate in terms of the uncoupled basis. So uncoupled basis is the orbital quantum number and spin quantum number and corresponding magnetic quantum number. So it should be expanded like these coefficients. So this calculation is very difficult and also very tedious. It is already calculated by the Clebsch-Gordon. We call it as a Clebsch-Gordon expansion. And one example of the Clebsch-Gordon expansion is that here hydrogen 2p state. In this case, L equal 2, L equal 1, S equal to 1/2. So here it is as coupling has the 3/2 and 1/2. In the 3/2 case, in the 4 possibilities, and the 1/2 case and 2 possibilities, and in each case, because magnetic quantum number and M1 is that ML is that L equal to 1. So 3 possibilities, 1, 0, -1, and corresponding 1, 0, -1, and there are 2 MS state, MS state, M2 state. MS state is a spin up and spin down case. So it is already calculated for the Clebsch-Gordon expansion, and it is a table. So one example of this 3/2, 1/2 expansion, and the non-zero term is that 1 orbital quantum number 1 and 1/2 spin, and the corresponding magnetic quantum number has the 1 -2 and 0 0/2. 1 -half and 0/2 coefficient expansion can be possible. So in the other example, we already in the same manner, and the non-zero term is coming from the magnetic quantum number, orbital quantum number, magnetic orbital quantum number, and spin quantum number is that 1 -1/2 and 0/2 case. So and the here. There are so many terms like this, and here because this Perturbed Hamiltonian makes that LG and SG, and LG we should have the expectation value, or all kinds of uncoupled bases. So and we should calculate the uncoupled basis in terms of the this Clebsch-Gordon coefficient. So and LG and the SG should be calculated like this, and also this relation in uncoupled basis and the LG expansion expectation and SG expectation like this, and LG applied to the ML and SG applied to the MS. So it should be normalized orthogonal case. So from these perspectives, and here one example, we calculated to the 3/2, 1/2 expectation on the another basis 1/2, 1/2. Then we singly calculated this term 3/2, 1/2, and 1/2, 1/2, and we calculated like this, and also like this, and this expectation for the coupled basis, it is coupled basis expectation should be calculated in each cases, and so many tables. But our interest is that J equal to 3/2 subspace and 1/2 subspace, and if this subspace it is not diagonalized, we should perform the diagonalization. But in this subspace already diagonalized, so well defined. Likewise, and also from this relation, also SG also can be calculated. SG also makes that eigenvalue h bar ms. So SG also calculated. So in this case also it makes that, and J and M state, J and MJ state, also 3/2 case, and 3/2, 1/2 minus 1/2 minus 3/2. 3 half, 3 half, 3 half case. And also it is j equal to 1 half case, and the two possibilities 1 half minus 1 half. And also the other here is a mj case, also 3 half case, 3 half case, 3 half, 1 half minus 1 half minus 3 half. For j equal to 1 half case, it is 1 half minus 1 half. So likewise, this calculation also very tedious, and I do not calculate anymore. Then the result is like this: 1 half 0 0 0 0 1 6 0 0 0 0 minus 1 6 0 0 0 0 minus 1 half. It is the j equal to 3 half subspace. The other term is 0 0 minus square root 2 third 0 0 minus square root 2 third 0 0 and 0 minus square root 2 third 0 0 0 0 minus square root 2 third 0 minus 1 6th 0 0 1 6th. Here it is j equal to 1 half subspace, and we are interested in the j equal to these two subspace. It is also diagonalized. Then it is very we already calculated LG matrix. It is a matrix, and SG matrix, and we should calculate we should keep in mind the Gman Hamiltonian. Gman perturbed Hamiltonian is that the mu b over h bar in the GLLG. Here let's omit the GL equal to 1, and the GE is the 2, SG, and it is perturbed Hamiltonian. So, and this anyway, this also matrix, and this also matrix. So then we should calculate we should calculate like this. For example, for j equal to 3 half subspace, j equal to 3 subspace, is LG LG equal to h bar. It is only for the 3 half subspace, and SG is that SG h bar. So multiply 2. So we should consider for the LG plus 2 SG. 2 means that 1 third minus 1 third minus 1 and plus. Then this matrix H bar cancel with each other. H bar cancel with each other. So this Hamiltonian is that the mu b b and the 1 plus 1 2 and the 1/3 the 1/3 because multiply 2, so and minus 1/3 and minus 1 and minus 1, and all other terms are diagonalized 0. It is perturbed Hamiltonian. It means that there are Zeeman energy shift. Zeeman energy shift, one is that 2 mu b, like 2/3 mu b, not minus, minus 2/3 mu b and minus 2 mu b. And there are four kinds of energy level splitting. Four kinds of energy level splitting. It is J equal to 3 half subspace, and we let's keep in mind that it is V also 2p state. For hydrogen 2p state, and so there are another one is that the one half subspace. In the one half subspace and the Lg. There is one half subspace. H bar and SG H bar. This is subspace J equal to one half subspace. So Hg prime for one half subspace is that mu bb, and so 2/3 minus 1/3. It is that 1/3 minus 2/3 and 1/3 is that minus 1/3 and 0, 0. It is 2 subspace, and it corresponding to the 1/3 mu bb and minus 1/3 mu bb, and there are these two kinds of energy. So and here, and when we make a draw the line energy and the 2p state, there are 2p 1/2 2p 1/2 case, the 2p 1/2 case, and 2 energy level, and here 2p 2/3 state and 4 energy level, 1 2 3 4, and it is when you consider for the spin, the energy level splitting is like this, and it is corresponding to the 2 mu b like this. So and it is a little bit different from the normal Zeeman effect. In the normal Zeeman effect, and there are only 3 possibilities, and one is that mu b 0 minus mu b, but in this case, and the anomalous Zeeman effect with considering the spin, and for 2p state and various kinds of spin structure can be expected.